Mm. Right one. Nope. Okay, we're gonna start. Maybe. Good. So, as I mentioned, it's winter holidays, so we have special guests. I might have to attend to them from time to time, but they usually behave quite well. They've been trying this for quite a few years now. Okay, so what we're gonna do today is last week we were working on the matching pennies, and we developed some ideas on how we could think of the strategies and mechanism underlying playing the matching pennies game. And what we're going to do today is to make a couple of examples of how we would formalize those and code them in R. But before we go there, are there questions? Everything was super clear. Yes.
Just regarding the assignments.
Yes.
For example, we have to in or we get introduced to.
So we're going to be talking about that tomorrow. That's the practical exercise. You already started developing with your groups the verbal theories, right? And tomorrow we're going to be working on you formalizing some verbal theories into code. And then the idea is that unless you feel you would need more time, then by next week you would have an assignment. Yeah. Does that make sense? Yeah. It's also a way of getting something out, right? You get that done, you wrap up that, and then we move on to the next step. Good. Has anybody looked at the course notes? Yes. Were they useful? Okay, good. So generally, like last week, I went through all the pizza fantastic modeling. All of that is reported in the course notes, right? So if there was anything that you would want to check or stuff, it's there. All the code that I'm going to present today, it's in the course notes. I need to check if I'm using the right microphone because I forgot to check. So I can move around the room. Settings. Audio. And I was using the wrong one. Okay. Yes. Share. Good. So last week we did the introduction to cognitive modeling. We looked at potential cognitive models underlying the matching pennies game. This week there is a short recap. There's how do we formalize generative models of cognitive agents? This word generative is something that's very frequent these days when we talk about generative AI, but it has a long history. It's basically a model that can produce the kind of behavior and outcome that you have. That would make sense even in principle to run simulations from the model
to get an idea of the phenomenon that you're observing. Right? And this can be done with any model, but it's more about the focus, right? So you build the model so that even before you fit it to the data, you can actually gain some meaningful insight about the phenomenon you're studying just by running simulations. That's not usually something that we get to do when we run a t-test or a regression model, right? We don't run simulations to understand the phenomenon better before we feed it to the data, right? And what did we learn? Some key ideas. Well, there's behaviors, but underlying the behaviors, there are different kinds of processes that we don't have direct access to, but we can hypothesize and test and corroborate with a multiplicity of sources of evidence. We can formalize these processes, for instance, learning, to make better sense of behavior, and then we can compare and develop the models. And that, as we will see throughout this course, there are structured workflows to make formalization manageable, transparent, and stress tests so that we are sure that we fully understand the implications of the models that we are running and that we the models are doing exactly what we think they're doing. And then we discussed that by formalizing the models, we put your thoughts, science out there, open to critiques and falsification and community development, right? So it's much easier to do that than having these fluffy words on there. My favorite example is something that I worked a lot on. That's the interactive alignment model. Do you know that? So the idea is that how do we coordinate with each other, right? It's very complex. But one of the tools, one of the mechanisms that we use to do that is we reuse each other's words, syntax, tone of voice, sometimes even accent. And by making each other, by making ourselves more similar to each other, we reduce the load, the cognitive load that is needed to process. We make ourselves easier to understand and the other easier to understand. And there is this whole line of research by Pickering and Garrett, two actually very good researchers, saying, as this works by priming, by processing what Balazs is saying, use the same processes, let's keep it very vague, that we would use to produce the same words. And therefore, these processes are pre-activated, meaning that when then we go in and start speaking, it's the easiest path is go through Balazs words, right? That also means that if Balazs primes the words I want to use, right, with that comes also the syntax and the semantics, because all these processes are correlated. And by doing so, we make each other's easier to understand, and therefore we will coordinate better. And I have a bunch of studies where we actually show that the more people repeat each other's words and syntax and semantics, the worse they collaborate. And so I was presenting these results to Garrett, and he was just thinking a bit and was saying, oh, but that fits perfectly with our theory, right? Because it's just that as you align via words the semantic aspect, then you don't need to repeat the words anymore. Right? And then I was saying, well, but what about the semantics? The semantic is also the more it's aligned, the worse. And he was, well, because there might be like a more abstract semantic called the situation models. That's what get aligned. We have the same idea of the situation. Therefore, we don't even need to reuse the same semantic things, right? And it does make sense, except it was nowhere implied in the original theory, and there is no way of falsify that theory, right? By formalizing it, it's not to say that theory wasn't important, but we can actually say, well, in that specific theory, these wasn't implied. We need to add something else. How do we formalize it? And by formalizing, we can put also some conditions at which this would not be a good theory, right? It would need to be changed. So from the matching pennies notes, we saw that when we describe strategies and cognitive processes, there are some categories to keep in mind. Some of these processes can be explicit, right? We saw Emily saying, I'm going to keep playing right and see how far I can pull it off, right? Or we can have strategies that are more implicit, right? I might sort of implicitly process how many times you're using right and then sort of say, oh, she's using right a lot, then I should keep right, and then I'll move to left when she doesn't, but then I'll go back again to right? But without really thinking of that. And that relates also to the participant versus researcher dichotomy, where it's always very important to debrief, first participate to your own experiments, at least in the pilot phase, and debrief the participants to figure out what they were doing. That gives you very valuable insight. It doesn't mean that it's the ground truth, because we're not always aware of what we're doing. We usually get good insight, but we shouldn't take that as the actual model. We saw the specific example of heuristic that a lot of the schizophrenia patients that we were testing for a task that we will deal with when we do weighted Bayes models, they would say, well, I actually don't process the whole data. I only look at this part of the data. And then if I'm in doubt from this part of the data, I access the rest of the data. Otherwise, I don't even look at that, right? And that's quite important to know. Of course, it doesn't mean that's actually what they're doing, but it is a good hint that that might be what they're doing. We also looked at a bunch of strategies from your discussions. A random agent that could be biased or not, meaning picking left and right completely at random or with a propensity in one side or the other. We looked at memory approaches, for instance, a one-step memory approach that only remembers the first step. For instance, the win, stay, lose, shift. If I guessed, I'll keep playing the same hand. If I didn't guess, I'll shift hand. We said, well, that doesn't need to be like that. We might have n steps. So we might have an averaging across previous n steps. We also discussed that from what we know about memory, there is an exponential decay of memory that could be modeled by putting an exponential decay function on this previous n step, or use a mathematically elegant formulation that's reinforcement learning. I added some slides on reinforcement learning for next week so that we can see it more in detail, because you didn't do that much of the math of it, right? Did you or no? Yeah, good. We also saw that these models tend to forget that we actually make models of the word. So we might even have models that assume that the other is making a model of the word and tries to infer which parameters they're using to build these models. That's the theory of mind. We have a theory of what is in the other person's mind, and we can go many levels of hierarchical development where I can assume that you have a model of the way I am dealing with this game. Or I can assume that you have a model of the way I make a model of you having a model, right? And so on and so forth. And if you want to dig deeper into that field, we're not going to deal with those specific models in the lectures, but there is the paper Thumbs Up that goes through all the details, both the mathematical and implementation of how to do that. Why we're not doing that? Because I don't hate you, right? We don't want to get bogged down in very complex models that require some tricks very early on. We'll start simply. Another example is the hierarchical Gaussian filter that you probably have been exposed to. It's basically a reinforcement learning in a Bayesian fashion that doesn't just make a model of the value of picking a choice compared to the other. It actually makes a model of how much these value might change over time and how fast the rate of change of the value over time might be, right? It's a hierarchical model. We might discuss some details of that a bit later. We also discussed that there's two different things. One is the estimation, and the other is the decision. Did you discuss this dichotomy in decision making? So let's say that I played with Lauritz and my cognitive system is really good at precisely estimate the probability that he'll pick right next time. That doesn't mean that I'll implement a decision that deterministically follows from his, right? That might be because I didn't pay attention, because I make a mistake. I say left when I wanted to say right. That happens. It might also simply mean that I have a temperature parameter in a more conceptual sense, meaning that I know that it's only going to pick right 80% of the time. So I might actually add some noise there, right? And these two steps are quite important to model separately in the models that we do. We also discussed, maybe not that much, but a tiny bit, that we should always try to remember what the heck we're trying to do. It's very easy to get lost in the details of cognitive modeling or any statistical analysis, but we should always keep in mind what we're trying to do. Are we trying to explain and perhaps predict these very specific behavior in these very specific tasks, which is a very legitimate enterprise, or are we trying to increase our understanding of cognition, right? So for instance, we might get bogged down into talking to all of you, trying to figure out the exact strategy that you were doing, and then trying to implement all of these different ways of playing the matching pennies game. And that would tell us something about the specific individuals here, right? We can fit the data better and better the more nuanced and decision tree we make our modeling. But how does that impact our understanding of cognition more in general? Or, if we're using these to investigate sociocognitive abilities in a specific population, how much does that increase our ability to understand that? This is something of a red thread throughout the course, right? At this stage, we're focused on giving you the basic competence, but we will see in the next examples that, for instance, we will take an existing model and we will try to get it to an existing model that has a theoretical impact, the idea that the mind is a Bayesian machine, and we'll try to see what are the implications for these specific tasks. Like, can we take these general principles and use them to explain these tasks better and see what they're challenged in terms of the general theory? Or on the contrary, say, well, these are the models that are out there, but really we think that our task is challenging this way of conceptualizing categorization processes. That will be the issue. So we should develop a model that actually tell us something more about the way we think that categorization is happening. Okay. I think I've just said these. And this is something that I was mentioning just as a fun thing. I was looking at some data from the very first year I ran the matching pennies, where I had people playing it against a computer that was running a theory of mind algorithm at different level of complexity. And 0 is when you're basically at chance. And so let's say when we have the algorithm is playing a random agent, CogSci students are pretty good at picking it up, right? No matter whether they're playing the matcher or the mismatcher. When they're doing, I can't remember what -1 was it, but let's say 0 is the reinforcement learning algorithm. They're already a chance. If the algorithm is playing a one-level theory of mind, so conceptualizing the CogSci students as a reinforcement learning algorithm, they're pretty much a chance. And level 2, they're actually below chance, right? So it's non-trivial. This also tells us that probably the CogSci students of those years weren't playing a sophisticated theory of mind game, which would have been otherwise something that we think, that's actually the obvious modeling choice for that task. Okay, we'll start simple. Today we'll see the biased agents. They're extremely simple, the random biased agents. but it's more a way of building your competences up, right? We will then apply them to more fun models like reinforcement learning, Bayesian information integration, psychometric function, drift diffusion models, and categorization. So we can start. I'm also noting that some of these code could be written in a more beautiful way. It's written the way it is mostly for pedagogical reasons. A bit probably because you can code better than me, but it's trying to be as clear as possible. So I'm not asking you to code the same way as I do, but I think that this way of presenting the code is helpful. Some of you will also say this is boring. Let's move further. We want to get everybody at the same pace, and also it's more about the workflow than the code per se. So the assignment that you will have to submit is about to create a document, Google Doc, a Word, and a GitHub repository. And in the document, you need to describe 2 possible strategies to play the matching pennies game in words. Include a discussion as to whether they include cognitive constraints. That is, for instance, a discussion of memory limits and their impact on strategy or other important science-driven considerations. You need to report the formalization of these strategies. That is a diagram and or line of codes implementing the strategies. If you report a diagram, it doesn't mean that you don't need to write the code. It just means that the code is on GitHub. And then you need to include plots of how the strategies fare against each other or other baselines, right? I should have updated that according to the instructions that we will see tomorrow. And a very brief discussion of what the plots allow you to understand. And then you need to put a GitHub repository. And what we're going to do today is we're going to go through how you could do the random agent strategy. Yeah, it's just a formality, but the GitHub repository must be linked in the document and must include all the code for the strategy implementation, simulation of agents playing with those strategies, and visualization of the plots. And again, this separation between the document and the GitHub repository is to help you sort of both focus on the code at a certain point, but also focus on the communication at a different point. I think we discussed these already. But we better understand the model. We can simulate results and understand implications. But also we get ready to do inverse inference next week. That is, we are able to see the formal function that generates data, which are the parameters. We can generate data according to those parameters. That means we're halfway towards fitting a model to that. We just need to translate that function into Stan, and we have data that we can test the Stan model on. And by formalizing, we can plan analysis, we can program experiments, etc., etc. So when we play the matching pennies game, right, and now we start thinking in terms of formalization, what would a computer agent need to know in order to play the game? Right, imagine you're writing 3 lines of code that play the game. What is the input of that code? Yes? Yes. So it needs to know what it can do, right? So it needs to have a couple of actions, for instance. Yes. Yes. Yeah. Yeah. So there's an action space. There's some sort of storage, memory. Yes. Uh-huh. Yes, but I guess these would be the action space, right? Yes. Yes. I think there's now it's okay, yes. So for some models, at least you want an updating strategy. I think we're actually missing a really basic thing that the agent should know in terms of planning its action. Yes. Hmm. Yeah, I think I would put that in the action space. Yeah, because in both cases, it's just a 0 or a 1, right? Yeah. So I think that it needs to be able to get some input, right? Which should be in terms, for instance, of feedback plus previous action, or it could be simply in which one was right, right? Right answer. Yes. So we need an input, previous choice, the opponent's previous choice, and the feedback. This information is kind of redundant, right? So we might actually boil it down to one of those two things, for instance. We need an internal mechanism that turns the input into a prediction of what to play, which could be something like this. And we need a decision mechanism, which we hadn't written. That turns the prediction into a choice. So in a sense, we could say that there is, an input. We have an estimation process, whatever that means, which fits into a decision rule or decision mechanism. And I guess that will turn into an output. And here we might have something very complex or something very simple. Does that make sense? Good. So we have an output, which is generated by an agent function, which needs to be given some inputs. And if the model has parameters, for instance, the bias of the agent or the learning rate of a reinforcement learning agent or what have you, the level of recursion of the theory of mind are given here. Right? And then we need to write some code in terms of how the input and the parameters are combined in terms of generating a decision. I don't know, are you familiar on the functional versus object-oriented programming distinction? So what I'm going to present throughout these course is a functional approach. So we write functions. It would be equally good to write objects, which I think Lauritz was kind of thinking on the lines of. That would be perfectly great for the portfolio assignments. I think that in R, it's still much more intuitive to code using functions, and that's why I coded it that way. Right, so we can take the very first example, our random agent function, which will receive input and parameters. So what do you think that the parameters of the random agent are going to be? Yes? Yeah. Okay, yeah. So let's imagine that since we want to build something that can play iteratively, we're only going to do one trial at a time, because for more complex models, they will change their own internal states on a trial by trial base. Yes? Yeah. So in the random agent, really, in terms of parameters, in terms of the latent variables that we might want to estimate from real data, the latent switches that we can use to influence the behavior of the agent, bias, the propensity to pick right no matter what, is the most basic parameter. Right? And then we can put inside what Lauritz was saying as the rule or action space. So here we have that we have a function for the random agent that we call random agent f, because I like to remember that stuff are functions. We define it as a function. We say that it should have two things that we provide it. One is the input, and the other is the bias. That's the parameter that we're using. And the choice of the random agent is simply sampled at random from a binomial distribution with an n of 1, a trial by trial base. I can't remember which one is the n of 1 and which one, how many times we do. I think the first time is how many, we only sample once, and we only try to answer one trial at a time. And then we have a bias or rate or theta. Those are all common words used for this, which tells us whether there is a inbuilt propensity of the agent to pick right more than left, and of how much. And then we return the choice. Right? That's going to be, since this is a binomial function, a 0 or a 1, right? Which we then can map on the meaningful action space of our game that is left or right. Is this clear? Right? I know you've done some functional coding. I'm going slow, but please ask questions if there are questions. In this specific case, we could remove input because the function is not really using input, right? It's probably a good idea to keep it in so we can make it more consistent with the other agents, but it doesn't hurt to take it out, right? Yes. Okay, what is this agent doing? Let's try to figure it out. In this case, it's easy to think it through, but it's not easy when we get to more complex models. We give it a rate, 0.5. We run the function. So we say the random agent function should receive the rate and produce the output random choice. And then we can say random choice, and that displays the choice. So we can say, how would it do in 120 trials? We create an empty vector that just repeats NAs as many times as the trials. Yes? Yes. Yes. So here we have a space between 0 and 1. And a rate of 0 means that we will never, ever, ever pick a 1. A rate of 1 means that everything you get out of the function is ones, or right hands, right? If we move in this space, we get probabilities of picking right. So 0.2 would means that out of 1,000 trials, 200 would be right or ones. Yes, exactly. It's a bias, it's rate, it's a theta. Those are all words that are used in the field, and I'll be trying to use all three of them so that you get used that they are exchangeable with each other. Thanks for the question, because I know that these different words tend to get people confused. Then what we do, since we want to play it in a way that's a trial by trial base, we can use a loop and say for t in the sequence of trials, right, which takes the number of trials, 120, and creates a sequence that starts from 1 and goes all the way up to 120. So we're basically saying repeat these 120 times. The random choice at time t is determined by the random agent function with that given rate. Right? Which means that we end up with a vector of 120 ones and zeros. We can make it into a data frame so that we can more easily represent it, right? Where we record which trial we're working with and what's the random choice at that, or the choice at that trial. Then we can do a ggplot, right? You're all familiar with ggplot, right? You put the data, you put the aesthetics, the y and the x. The x is trial, so we have time on the x-axis. The y is choice, so whether they're choosing 0 or 1. We say just plot a line so we can follow it over time, and use theme classic because I hate the gray background of the default theme. And then we look at the plot. You see much from that. Right? That's the problem with binomial things, right? We can see something. We'll see that actually as we vary the rate, we're going to see different structures. It's not very pretty. I should move these out of the way. What about different rates, right? Well, what we can do, right, since we're programming, it's pretty easy to automate this, right, to make it into a loop. We can do better. We'll see parallelization at a later class. Now we're doing loops. So we're going to say that we're going to try all rates in a sequence between 0 and 1, going in steps of 0.1. So 0, 0.1, 0.2, 0.3, 0.4. We create a random choice vector for each rate. We do exactly the same loop as before, moving through each of the trials, generating a random choice at times t for that rate. We create a temporary table with which trial we're at, which choice has been made, and what was the rate that generated the process. And then again, we can save it. If D1 already exists, we simply add temp to whatever was there. If it didn't exist, if it's the first rate we're testing, we just create a new D1, right? Then we can create a ggplot exactly like before, but we're saying, please split the plot in a bunch of facets according to the rate. Right? It's not super pretty. It's not going to win a visualization award, but we are seeing something there, right? What are we seeing? Well, let's try somebody else. Yeah. Yes, Victoria? Yeah, exactly. Yeah, exactly. So it's really reflecting the rate, right? And the thicker the plot in the middle, the more switches there are. The less thick, then we need to actually look at where the rate is. And this is actually a nice sanity check because bugs are everywhere, right? We want to check that things are done. If we code it by hand, bugs are everywhere. If we ask ChatGPT or Cursor AI or whoever to write it for us, it's even more crucial to check because bugs just creep in everywhere. It doesn't understand what it's trying to do. It's very good, but it doesn't understand, right? Okay, do you have better ideas on how to improve this representation? Yes? Yes? I hate bar plots, but that's a good idea, right? Because here times doesn't matter really. Yeah. Yeah. So this is a very good solution. I don't think it scales up to the next models where we want to look at temporal stuff. So yes. Okay, yeah. And how would you do that? Yes. So basically, what you're saying is, well, instead of looking at 0 and 1, we could look at the percentage, the proportion of the times that um, 1 has been chosen, given the amount of trials that we are at, right? So a cumulative probability of picking 1. So this is what we're going to do. We say we take D1. We say keep things separated by rate, because we don't want to accumulate across different runs of the simulation. Create a new variable, which is called cumulative rate, which basically says cumulative sum of choice. What is this doing? It's saying basically how many choices have been made so far. In the first trial, it's 1. In the second trial, it's 2. In the third trial, it's 3. No, sorry. The cumulative sum of choice, and choice can be 0 and 1, right? It's saying how many times has 1 been chosen so far. And that tells you 1 has been chosen 3 times or 4 times or 100 times. And these sequence along, it's basically saying how many trials have there been so far. So 1, 2, 3, 4, 5. Which means that on a trial by trial base, we can say so far, what's the proportion of ones that have happened given the amount of trials that we went through. Then we do a plot, which is just like before, but now we're saying as the x-axis we have trial, as the y-axis we have cumulative rate. We still use a geom line, and we add a horizontal line to tell us where the chance, or if there were no bias, where we would expect things to be. We put it limits at 0 and 1 because it wasn't looking pretty, and then we separate the plot by rate. We visualize. Is this more informative? Tiny bit. I think it gives us a much better picture of what's going on. It's more precise. Can we do it better? Well, we are not using the space in a very efficient way, right? There's lots of white space. So we can, and there's the code, right? Just put all of them in the same plot. I know this is very basic. Bear with me. We're going step by step. So here we can actually see We could have put labels. I'll do that maybe next time. But as we increase rate, at the beginning it's very messy, but very quickly it's settled in a clear rank. Right? And especially when we'll start adding noise, it can tell us something quite important about when should we expect the behavior to be inferable. Right? Does anybody have the time? I don't have my mobile to check. Oh, it's perfect. 1. Okay. So good. Let's take a break. Here. Okay, we should restart. Oh, you can stay. Okay, so now we made that specific model, right? Does it make sense to add memory? So we can do that in different ways. We can add a moving average. We can add an optimal Bayesian update. We could do a weighted Bayesian update, right? What am I talking about here? I'm anticipating some stuff, but the basic idea is that we have a belief about how strongly propense Emily is to pick right. And in the last round, she picked left, right? How should I integrate that in my memory? Which kind of weight should it have compared to the last 10 trials where she picked right? And the optimal Bayesian updates would make her last behavior count as 1 in 10. Right? But a weighted Bayesian update might simply say, well, actually, these might be the hint of a change in strategy. I should give it a higher weight. And we could do reinforcement learning, right? Which is, in a sense, something that has been developed and simmered across the years to represent in a good way how these weights change. Pargoli, Tristan, Tristan, Tristan. Yes, sorry. Okay, which is basically this idea, right, of a weighted Bayesian update, where we have that the value at any given time t is equal to the value at times t minus 1 plus predictive error, right, which is my choice and the feedback that it has gotten, weighted according to a parameter called learning rate, alpha, which can go between 0 and 1. Normally, 0 means that you don't learn shit. 1 means that you forget everything and just learn from the previous trial. Another way is we could add errors, right? We've been discussing. So, for instance, we could have a different function, which is the random agent noise that has a rate and has a noise. Now it has 2 parameters, right? The choice is generated by a binomial, just like before, at a given rate. But if a noise process, another binomial with a rate of introducing noise, which is given by the parameter noise, is equal to 1, then instead of using the previous rule, we're actually picking completely at random, right? Which reflects, for instance, if the participant is distracted, it's not that necessarily they're going to pick the opposite of what they would have picked whether they were, if they were paying attention. It's just they panic and just go for one or the other, right? And then we can return the choice. Does this make sense? Again, this is very simple, and there's something a bit odd in having a random function here and then adding a noise with another random function. But that's because we're building on the simplest possible model, number one. And second, we'll see in a couple of slides that these actually has important implications for stuff like statistical power, our ability to see patterns, etc., etc. Right? So we implement it to observe the implication of the model that we're building. We create a new data set called D2. And now we have a nested loop. So first, we loop through different levels of noise, right? And we're going to say that the noise starts at 0, no noise. It should be exactly like before. It should get up to 0.5. 50% of the trials will noise seems kind of a high threshold, right? We're really fucked if that's the kind of experiments we have. And, well, unless you work with kids. And we go in steps of 0.1. The loop inside is exactly the same. So it's then looping through the different possible rates, except that we have the random agent noise function inside, and that we're saving the noise parameters so we know how the data were generated. Does it make sense? Right. So we're going to have, I think it's 6 levels of noise, each of them for 11 rates. Then we can create our cumulative rate by rate and noise so that we can split those aspects. We can plot it. And then the only difference here is that we color by rate, by bias, by theta, and we facet wrap by noise. We visualize that. And actually, even if the model is kind of trivial, this is actually quite, it's telling us something about which kind of pattern we should expect in the data given different levels of noise, which can allow us to assess the level of noise in the data. It also tells us something about, in a sense, statistical power. What do you see when you look at this? Yes,
It's more like
the higher the noise. Yes, yes, exactly. Why?
because the rate is centralized.
Well, it's because it's basically says so you would expect this one to be all the way up here, right? But 50% of the time, it's not going to follow that rule, which means that out of 120 trials, 60 are completely random, which means that out of those 60 trials, if the sampling is average, we were going to get that 30 are going to be zeros, right? And so even if it's supposed to be here, it will stabilize at 0.7. So the higher the noise, the more centralized our propensities are, which has a consequence, right? That the difference between different biases is harder to see, which is exactly what we mean when we say that we should be very careful in our studies about measurement error, because measurement error fucks your statistics up, right? It makes it really hard to see the patterns. It makes it harder for the models to reach confidence in their conclusions. Sometimes, though, we actually introduce measurement error on purpose. And we need to be able to think through what we're doing to the data and how to infer things back. When do we add measurement error? So let's say that I'm asking you very sensitive questions about, for instance, what's your favorite teacher at Kotsai, or that sort of things. And you don't want, your participants to lie or not respond. But at the same time, you're worried that your participants might not feel like answering correctly, or in a very bad case, when the Cogsci police comes here, right? If you said that you, I don't know, like me best as a teacher, they'll bring you to Cogsci jail because, Josh doesn't like that, right? And he's that kind of tyrannical head of department. But joke aside, right, imagine sexual orientation, political orientation, religious orientation. If these data got out, it might be a problem in certain contexts. So you actually have the system that every or at random with a certain probability will change the answer that people are giving. And the participants are aware of this. This is also something that Meta does a lot. At least they report that they do that a lot in their differential privacy system. And so that even if somebody gets your data and says, well, Sabrina really likes Mark of all teachers best. What is about that, right? Then you can say, well, this is a chance, right? You can't really give me the responsibility because some of these answers are a chance. You can't hold me to those legally. But then you want to know what's the propensity of these to happen so that you can actually include that in the model, as we will do, and you will be able to get slightly more confident inferences at the population level, not at Sabrina's level. Another thing that we should be aware of is that with increasing measurement error, it takes more trials to get to a clear pattern, which is exactly what underlies the notions of statistical power that you discussed in previous courses. I think we discussed it in method 3, meaning that you need a certain amount of data to reliably infer the patterns. And the more measurement error there is, the more data you need. Here, it only, actually, depending on how much precise you want your inference to be, but it takes at least 75 trials to not get biases that are 2 steps aside switched. And it takes more if you don't want biases that are 1 step aside switched. Actually, I don't think you can do that reliably with 120 trials. So just by doing this, you start getting a much better insight of what you can do with the kind of experiments or data that you will have. Now we've done the easy part. So what about a responsive agent? Right? The agent that we built was just playing at random. It didn't need the input. We even removed it from the function for simplicity. Right? So we formalized the Win-Stay-Lewis shift. This is the Win-Stay-Lewis shift agent, which has as input the previous choice and the feedback. Those are both inputs. We don't have a parameter. Why don't we have a parameter? Yes, Victoria? Because there's no probabilistic element, right? Now we're taking the simplest possible Win-Stay-Lewis shift. Now we're going to say, if the feedback is equal 1, we take the previous choice. If the feedback was equal 0, we take 1 minus the previous choice. Right? 1 minus 0 is 1. 1 minus 1 is 0. So it flips. Okay, now we test it. We give the Win-Stay-Lewis shift a previous choice of 1 and a feedback of 0. What do we expect as its choice? It's not a trick question. Yes, exactly. Because it picked one before it lost, we expect it to shift. Good. Now we set up the sequence just as before. We put it against an agent, right? We cannot have it play on its own because it's a win, stay, lose, shift. It has to win or lose. We pick a agent with a rate of 0.7 so we can more clearly see some patterns, right? Self, we create a empty vector for the choices of the agent on which we focus, the win, stay, lose, shift. Other, we create an empty vector for the choices of the other agent. We say that even the win, stay, lose, shift, the first time is just going to play random because it doesn't have a previous choice. Right? We can implement that in the function, but this was to keep it simple. Then we say that for t in the sequence of trials, so for every trial, since the random agent is not responsive, we just pre-generate all the data. But for the win, stay, lose, shift, we start at the second trial because the first one was the random one. We go through all the trial and we say, if the previous self choice was equal to the previous other choice, then the feedback is equal 1. Otherwise, the feedback is equal 0. And then the choice of self at this time is given by the functions that we've seen, the previous self choice, and the feedback that we just calculated. Does it make sense? Is it too simple? Is it useful? Good. We visualize it as before, like our first attempt with 2 different colors. And I kind of like the psychedelic nature of this stuff, but I can see it's really hard to see what's going on. But basically, you see that there is one agent, that's the red agent, that's always in front. And there is a blue agent that follows it. Which one is the win, stay, lose, shift? Yes. Nope, because the red leads. The win, stay, lose, shift always follow, right? So it's the blue one. This is the code. We don't need to go through that because it's really nothing else but what we've seen before. Yes? So the win state, oh. What did I do that? Trial self is red. You're right. But I'm seeing isn't the red always leading? I need to double check. Yes. I'll double check and let you know. But generally what we expect to see is the win, stay, lose, shift that follows the choice of the random bias, right? How about performance? We again do the cumulative self and the cumulative other. And the self should be in red and the other should be in blue. And what we see here is that it's really hard for these agents to win. But there is the blue agent, which is the random opponent, which is slightly at an advantage. Why is it slightly on an advantage? Because it doesn't care what the win, stay, lose, shift does. It shifts at random, and whenever it shifts at random, it wins. So paradoxically, the more random the bias agent is, the better it will perform. Right? because the win-stay-lose shift is not going to be able to rely on a sequence of several ones or a sequence of several zeros. Sometimes it's better to play random. So here we can see with different rates how well the random agent is playing, right? No, sorry. With different rates of the random agent, how well the win-stay-lose shift agent is playing, which is the flip of what I was saying before. The more random it is, the less the win-stay-lose shift performs. The less random the random agent is, the better the win-stay-lose shift performs, right? There's more structure to learn from. We can make it play against itself or against another version of itself. Here, the code is slightly more complex, but that's why we're building it one step at a time. We have a vector for self, a vector for other. We initialize both of them at random. And then from the second trial, we are going to say that itself, previous self is equal to previous other, then the feedback is 1. Otherwise, it's 0. The self is exactly like before. The choice of self at time I is the win-stay-lose shift agent determined by the previous self choice and the feedback, while the other is the win-stay-lose shift agent with the previous other choice, their own choice, of course, and 1 minus feedback. Why? Because it's a zero-sum game, meaning that if one wins, the other loses. And that's endless source of bugs when we do these kind of things, right? Just making sure that we put in the right feedback for the right agent. Then we can represent it, right? This was how it was against the random bias. And here, even more psychedelic, how it is against the win-stay-lose shift agent. Because they just keep crossing each other, right? Because I won, therefore I'm going to stick, but you lost, therefore you're going to shift. And then we switch. Right. And this is how the performance looks like. They're performing exactly equal and symmetric. Right? And they're just shifting. Now I win, now I lose. Now I win, now you lose. Sorry. Now I win, now I lose. Now I win, now I lose. Okay. Can we put cognitive constraints into the win-stay-lose shift? Right. Memory, it's kind of hard, right? We start moving very far away from the win-stay-lose shift, more into reinforcement learning territory. But errors, that's not a bad idea. How would you implement errors? There's at least 2 different ways. Yes, Sabrina? Mm-hmm. Yes. Okay, so there's 2 ways. One is exactly like we've seen before. We have a noise function that says no matter what you estimated to be the best choice, I'm going to pick at random n times, right? A certain proportion of the trials. The other is to say the win-stay-lose shift becomes probabilistic, right? When I win, I stay with a certain rate. When I lose, I stay with a certain rate. When I lose, I shift with a certain rate, right? Why am I discussing this? Because I want you to get a grasp of this whole idea of building models. There is no one way of doing that, right? You can think through what's the best way given what you're trying to do. And sometimes you'll still find 2, 3 ways and you don't know which one is best. And then the good idea is to try a bit and then pick one. Right? We can add noise, as I was saying, right? We add a noise level as a parameter. we add no matter what has been decided. If it goes through the noise function and it gets a 1, then it's going to pick at random. You can plot the impact. This is the behavior, and it's hard to see from there, but you can see that the perfect following is messed. Right now, it's a bit out of step. And the performance is actually better. Right? This is a funny, interesting case where you just add some random noise and the model is performing better. But of course, it's playing as if the opponent has a strategy, but the opponent has no strategy. So noise is better. So next step is all these processes are kind of random. They're probabilistic. We shouldn't trust just running one agent 120 trials and expect that that's going to be representative of everything. Also, we probably expect to test more than one participant. So it's good to have a data set that has multiple agents on which we can then fit our multi-level model and see if it works. So we scale it up to 100 agents. Right? There's two possibilities. They can be perfect clones of each other's. Right? We give them a rate of 0.7 to the random agents. Or we give them a noise level of 0.2 to the Winstay-Lewis shift agents. And that's it. Every agent is the same. Or we can model it as a population, right? We can say, actually, the noise level follows a uniform distribution between 0 and 0.15. Every time we generate a new agent, pick a number there. Does that make sense? Why would we do that? The plot is going to be more messy. Yes. Sometimes we run our simulations in a clean way. So we set the parameter, the probabilistic parameters for all the agents to be exactly the same. And then we run the 100 simulations, and then we see how it looks like. And it's still going to be different behaviors because it's probabilistic. Sometimes we actually pick the idea of having slightly different parameter values for each agent as extracted from a population. Yes. Yes, because when we'll move to empirical data, nobody is expected to have exactly the same parameter values as other people. So it reflects a slightly more realistic constraint, right? It messes up our analysis more, which means we're better prepared to deal with the uncertainty of the real world. We're not prepared, but we're better prepared than otherwise. Okay, we can loop through 100 pairs of agents, or we can make a function that simulates and saves a combination of one pair of agent and then parallelize the process. Have you gone through parallel? I know that many of you will know it already, but have you gone formally through parallelizations? So your computer, even if you're not working on uCloud, has n processor. I don't know, mine has 12, I think. And a trick in doing calculations that are repetitive is to split the process into different chunks and send them to ideally all 12 processors at the same time. So that your timing is going to be 12 times less. Or maybe there is a bit of overhead in dealing with putting things together, but let's say it might be 6 times faster, which is non-trivial. They go to a free school. They're not used to sit still. Yes. Okay, and we'll see that at a later stage. We'll actually go through the way of doing that. Am I done already? Have I cut it too short? How far are we? Okay. that hadn't happened to me to miscalculate, but lucky for you, I'm already ahead in preparing next week's class lecture. Which means you get a tiny bit of reinforcement learning already. Yes. Okay. Are there questions so far on the models that you've seen? Would you feel confident in running them? The trick is all the code is in the course notes, so you can actually run things as you work through the assignment. You can go there and get inspired by all the code. Yes. Yes. No. No, that's an excellent point. So there's many different ways of doing computational modeling or cognitive modeling. Sometimes you're just trying to make a qualitative point. For instance, I have a bunch of studies where we work on categorization, and there's a bit of spoiler on stuff that we're going to do. Basically, as you'll have to do, you meet a bunch of aliens, and you need to figure out which ones are dangerous and which are not. And then you have to learn some patterns that allow you to predict that. And there's a bunch of different models in the literature as to how we do that. One model is the exemplar model. Did you do categorization stuff in Intro to CogSci? But basically is Tristan, Nara, 10 minuti, poi andiamo. Però adesso dovete fare ancora i bravi. That as you go around in the world in your baby trolley, you see cats and you see dog, and then you look at your dad and say da, and then the dad says dog, right? So you have your box for dog, where there's these little doggy thingy that doesn't look a lot like a dog, but let's imagine it's a dog. And then you go around again and you say da, and you see, oh, there's a huge Great Dane. Right? And then you say da, but that time it's actually a cat. Right? And then you keep doing that until you have a few exemplars in each of your boxes, and then you're going to see, a Chihuahua, and you need to figure out whether it's a cat or a dog. And then you say, oh, how close is this to that? Well, let's say it's 0.7. And how close is this to that? Well, let's say it's 2.1. And how close is that to that? Well, let's say it's 1.1, right? And then the average between these two is 1.4, and here is 1.1. So you say these cat. Right? And so we have people running the experiment, and then we wanted to show that this was a terrible model for that. So we simply ran this model on the experimental setup a million times. We showed the band of performance of the algorithm, and then we show that participants are consistently above that. Which means that we're making the qualitative point that the mechanism, at least in the way it's formalized here, is not is not what's going on in humans. Does that make sense? Another case is I might implement a library to play the matching pennies for experimental purposes, right? And I implement a cognitive model that plays different strategies that are theoretically motivated to see how people react to them. I don't care, and in principle, I don't think that the participants are using those strategies. They're just cognitive agents designed to test certain ideas. Yes, does that make sense? I think there are other cases, but they're escaping me right now. We are going to do both because so you have the full thing, right? The full toolbox to do that. There's a case for especially with the heavy models, right? When they start having a lot of parameters that you can basically, as von Neumann said, right? With 4 parameters, I can fit an elephant to the model. And with 5 parameters, I can make it move its trunk. Meaning the more parameters you have, you can fit any sort of data. If we use the theory of mind models of 6 and 7 levels of recursion can fit anything you throw at them, no matter the generative mechanism. So there is a certain aesthetics in research of saying, try to keep your models simple or try to fix their parameters to meaningful terms and run simulations to compare to the data before you even fit them. Cool. Does it make sense? Do you have questions? So this is something that I'm just gonna give you a taste of because that could be one of the agents that you might want to implement tomorrow. Reinforcement learning is a good skill to have. Did you do any of it? In any course? Only theoretically. Okay, good. So I don't need to go too much into detail, but there's a key paper called The Theory of Pavlovian Conditioning, Variations in the Effectiveness of Reinforcement and Non-Reinforcement, that was developed by Raskolna and Wagner, relying on a lot of ideas that were out there in the field. It was not a new thing, even just the name Pavlovian, right? Referring to Pavlov. It became a huge thing to the point that I think in DeepMind, they have hired Richard Sutton, which is one of the key developers of the algorithm. And he published a few years ago the 2nd edition of his reinforcement learning handbook, which is really good. It's a huge field. And it owes its fame to the fact that it is a domain general mechanism, meaning it's about learning no matter what you're learning. And it has the very rare property that it triangulates across theory, behavior, and neural activity. So one of the reasons for which people really buy into that is that there has been neural experiments in which the data of the neural activations in the dopamine receptors follows exactly the predictions of the model. What are the predictions of the model? Well, you've seen it here. The value of a choice, right? How much you should pick a given choice is given by the value that you already attributed to that and by the predictive error. Meaning that if you already expect that opening the black box gives you a piece of cheese and you like cheese, by opening it and finding cheese, nothing really happened, right? Nothing changes. If you didn't expect cheese, you open the box and you find cheese, haven't had lunch, sorry. You are positively excited, right? It's a positive feedback. And you reinforce your expected value of picking the black box. But if you already expected cheese and you find cheese, no positive feedback. Right? And that's exactly what they find in the dopamine receptors, that the activity that they record with, I think it's actually electrode recording, implanted electrodes in cats' brains, is that If they give a reward, but the reward has been already learned, there is no extra activity. And so it became super popular. I think I just want to go for now to the key aspects, and then we'll pick it up again next week with the more conceptual aspects. There's two parameters that we have sneakily already seen them. One is the learning rate, or alpha, which is it moderates the impact of predictive error on the change in expected values. Higher learning rate is faster learning, but less memory. A high predictive error makes the expected value swing independently of previous experiences. Lower learning rate is slower learning, but more memory. And we can actually derive from the equation of the reinforcement learning the exponential decay, but we don't need to go through that now, and I already tormented you last week. But we can see with a simulation that if we change the learning rate and we put on the x-axis how much a given trial in the past matter for your current expected value. We have 7 trials before, 6, 5, 4, 3, 2, 1, and the current feedback that you got. Each line tells you the relative importance of each of the trials, which an alpha of 0.9, a high learning rate, you get that basically nothing beyond 2 trials ago matters. If you decrease the learning rate, you see that the past has a long, thin shadow, right? And the temperature is not in that equation because that equation is about the estimation of the value. The temperature is about the decision rule. It indicates how determine the choices by difference in expected values. So if value of choice 1 is 1 and value of choice 2 is 0, you could imagine to always pick 1. But the temperature is saying, wait a second. We don't always follow the best estimate. This is not usually interpreted in terms of disattention and noise that we've seen before, but it's often framed in terms of exploration exploitation, meaning it pays to every now and then try a new restaurant and not always the one that you like, because you might find something of higher value. This is something that's very useful when the environment changes, et cetera, et cetera. So it's a way of determining how deterministic the choice is. Funnily enough, right, the math doesn't care what the interpretation is. Distraction, exploration, exploitation, error, they're all subsumed into these terms, and it's really hard to discriminate between them. You need to do that by experimental means. I think, what's the time now? 55. Okay, great. How do we simulate that? Oh, this is bad contrast. But we have function called value update. We've seen it there. That takes a value, takes alpha, it takes the choice, and it takes the feedback. We have that the predictive error is feedback minus value, right? If we expected a value of 1 and we got a feedback of 1, nothing changes, no predictive error, everything is as expected. Any other combination gives us something different. If value is higher than feedback, we're pushed low. If feedback is higher than value, we're pushed high. We increase the value. Then we have 2 choices. In this case, we could generalize it to n choices, but binary because we're still doing the matching pennies. Value 1 plus alpha times 1 minus choice times feedback minus value. So what are we doing here? We have the value is like there. The feedback minus value is like there. The alpha is the learning rate. But here we have a 1 minus choice. And that's because if we're picking 1, that's choice number 2. So we don't want the value of picking 0 to be updated. We don't know what would have happened if we picked 0. Technically, we do in the matching pennies because they're exclusive. But let's imagine that you're going hunting for rabbits or you're going hunting for deers, right? You don't know what would have happened in the other case. So 1 minus choice is saying if the choice was 1, this goes to 0, and no changes in value happens. If instead we picked 0, 1 minus 0 is 1, so the update for choice 0 happens, but the update for choice 1 doesn't happen. Then we update those two values, and then we return the updated value. This is not the only possible way of thinking of things. So in the matching pennies, these two things are the opposite of the other. We don't need to update them separately. In many complex decision making, we still have something called the counterfactual reasoning, that we pick something, but we still get some cues about what would have happened with the other choice. So both values get updated, just according to different mechanisms. And that's where you can have a whole handbook about reinforcement learning, because there's a million different choices to make. And then we can use a softmax function, where basically we say that given a certain x, the estimated difference in value between 1 and 0, and a temperature tau, the propensity to pick, or the propensity to pick the outcome, to pick 1, is given by this formula, right? Which is just straight off any softmax definition. And with this, I'll close. Here you can see if you have the algorithm that always picks 1, so we can observe its changes in expected value without thinking what it has picked. We can say that the red is the feedback. It's high here, so we see the value going up. Then the feedback is -1, right? You picked the wrong choice. It was the wrong thing to pick 1, so it goes down, and accordingly, the predicted value, the expected value, goes down a bit or a lot. The other agent again picks the wrong according to your expectation, and then the expected value really reaches the bottom here, but then the other agent goes the other way, and then you can see that here it has a pretty high learning rate, so it's actually following it almost as a win, stay, lose shift, but it takes 2 trials to really believe in that. And that's where the reinforcement learning is the more general case of the win, stay, lose shift. With that, we'll stop, and tomorrow we'll get coding with whatever strategy you want to code.